Hello, everyone. Welcome back to the Double S YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Sarah Moran with us today. Hello, Sarah.
Hello, how are you?
I'm doing awesome on this October 30th, day before Halloween, 2024. It is cooling off in Phoenix, actually. So I'm in Phoenix, and we actually got down to 56 this morning, which is like lovely. Just great.
Oh,
But
it's here.
it'll heat up into the 80s or so today. So very lovely. And Sarah, what's your geolocation? Where are you at?
I am in Greenbelt, Maryland right now, NASA Goddard. And the trees are fully all in their fall beauty. But the
Cool.
temperature is relatively similar today.
Very cool. I think you were at Tucson before, right? That's where I remember
I was
your.
in I was in Tucson until August of this year,
Okay.
yes.
Okay. Yeah, because the article has a Tucson affiliation. So you're quite familiar with the Arizona weather. So very cool. And Sarah, what do you like to do for research?
So I study aerosols, so clouds, hazes, things that are in the atmosphere.
Cool.
I do that in the lab and models. I love when observers give me data to compare those things.
Ooh, so you're a
Do there.
triple threat here. You sort of observations, experiment, and theory.
I don't do the observations. I just
Okay.
gratefully accept them from my collaborators to compare against my models.
Okay, very cool. And that is going to bring us to this very awesome APJ letter. It is open access. It's the open access era. People, go grab a copy for free. Go get one. Neglected silicon dioxide polymorphs as clouds in substellar atmospheres. And Sarah, take us away.
Okay, so the title is actually an homage to a past article about neglected compositions of clouds and brown dwarfs. And so I'm narrowing in on just one composition, silicon dioxide, but I'm looking at all the polymorphs.
Okay, cool.
Polymorph just means many shapes. And so it's the idea you can have many different kinds of crystal structures that make up silicon dioxide as clouds in these atmospheres that people haven't really thought about for either brown dwarfs or exoplanets yet. And so
Mhm.
that's what this
Mm,
paper is all about.
cool. And that's what attracted me to the article. I was like, okay, let's hear about this one. Very cool.
Yeah. So I did this with Mark Marley, who was my postdoc advisor while I was at the University of Arizona. And he's an amazing mentor and person to collaborate with. And so I'm using a lot of the modeling infrastructure he has developed over the years.
Uh-huh.
And Sam Crossley is actually a brand new research scientist, or at least he was as of the spring, at the Lunar and Planetary Lab at the University of Arizona. And he is actually like a card carrying geologist, which Mark
Ooh.
and I are. And so we relied on him really heavily to make sure we weren't saying ridiculous things about polymorphs and about minerals throughout this paper.
Good shout out. Good shout out. Okay, let's go ahead and get into it here.
Okay, so the sort of introduction here is the idea that silicate clouds are a really critical part of lots of different kinds of substellar objects. So that includes brown dwarfs, and that's really where the field got started.
Mhm.
This little highlight here that brown is not a color was a contribution from Mark because that was really what started to set the stage for this field back in the 80s when
Yes.
model work and even when that modeling work was happening just from very simple thermodynamic arguments, you would expect
Yeah.
silicate to be the things that are condensing in these atmospheres, so the
Okay.
things that are acting as the clouds. And by the time we had a pretty robust set of theory for this from the 80s to the 90s, we then moved into the Spitzer era. And Spitzer could actually go and measure these silicate signatures directly in the mid-infrared.
Cool.
And so we did that for a whole bunch of different brown dwarfs, and people started to develop theories about the ways you would see the silicate features and whether or not they indicate a specific kind of silicate. You can have many different kinds of silicates.
Yeah. Okay.
Uh, and so that can be magnesium silicate, you can have calcium and iron bearing silicates,
Mm.
or mixtures in between. Um, and all of these have this really sharp feature
Yeah.
around 8 to 10 micron region.
All righty. Good. I'm with you.
So that was for brown dwarfs. As we started to get into the era of being able to characterize hot Jupiters with the Hubble Space Telescope, people realized we're in a very simpler temperature regime. They're about the same size of planets or objects. And so
Hmm.
we expect these clouds too to be in hot Jupiters. But by then we didn't have Spitzer's mid-infrared instruments online anymore because we lost the cryogenic capabilities. And so we were
Yes.
limited to like 3 and 4 microns instead of where these clouds exist.
Okay. Bummer.
But there were these predictions that they should be there. And I've mentioned all different kinds of silicate clouds, but really mostly what we expected was magnesium silicates, just based purely on the abundances of those
Yeah.
materials in these atmospheres. That's what we would expect the most.
Okay. Cool.
For those magnesium silicates, you can also start to think about the different kinds of shapes of the condensed particles. And there's sort of like two big picture ways you can think about that, either as glassy or amorphous particles or as crystalline particles.
Okay.
From a theory perspective, you would expect them to be crystalline because if you maintain high enough temperatures, things should crystallize and then stay as crystals. You'd really only expect the amorphous or glassy kind if you cool things off really quickly.
Okay. Quench it. Hmm.
By quenching it exactly.
Wow. Okay. Cool. I'm with you.
So if we skip down past this figure, which is a
Sure.
little clearer than I want to go yet.
That's all good. All good.
So there's this like sort of laboratory and theoretical basis where we expect crystalline features, but what we were seeing in all of these brown dwarfs was amorphous material. The observations looked amorphous instead, and so that was a tension point between theorists and observers if we were seeing one thing but expecting another.
Right.
And then the second thing to think about to set this all up is that silica or silicon dioxide, SiO2,
Mhm.
any way you want to say it, was sort of ignored as a potential cloud material because from thermochemical equilibrium, you don't expect it to be the dominant mass of cloud material.
Okay. Okay.
You
Hmm.
can make it if you think about non-equilibrium. So this concept of dirty grains where you
Yeah.
have precursor particles.
Okay.
But a lot of the field, other than these very few studies, mostly ignored it.
Okay. Hmm. All right. There's our two.
Had to stop ignoring it because there have been two sort of high profile detections of SiO2 clouds in substellar atmospheres recently. One
Hmm.
was brown dwarf, this paper led by Ben Birmingham in 2021. They
Yeah.
threw a just kind of ridiculous number of models at their data set and found that the best match very strongly needs SiO2 clouds in the mix.
Okay. Okay.
And
Mm.
then now with JWST online, particularly the mid-infrared instrument, we now have access to those mid-infrared wavelengths again, so we can go after these cloud features in hot Jupiters.
Cool.
And a couple of these that are suggestive have been made. I've listed here. So Miles et al. 2023, Dirac et al. 2024, and then Wellbanks et al. 2024. So looking at that same data set, maybe arguing with it. We'll ignore that for now.
Okay.
So they see this very broad feature in the 8 to 10
Mhm.
region, which says it's probably some sort of silicate, but we couldn't tell what kind.
Okay.
The really exciting thing is the detection in WAS17b, led by Grant et al.
Huh.
In 2023,
Yep.
where they see the signature in the mid-infrared in the JWST wavelengths, and it's very sharp, which means you can identify it pretty conclusively as SiO2.
Nice. Cool. Okay.
And so then that's
Mhm.
all kind of exciting. We have to start thinking about SiO2,
Sure.
and it turns out you can sort of solve this tension with the thermochemical equilibrium
Yeah.
if you just adjust the magnesium to silicon ratio a little bit. If you turn
Okay.
magnesium just enough, you start to make SiO2 in abundance that it's starting to compete with the magnesium silicates. And so
Okay.
that's like interesting chemistry that's really been driven a lot, that theoretical work, by the need for it from the observations.
Yeah. Okay.
And we have the amorphous versus crystalline. We have the different compositions that we're drawing from here. And so
Yes.
we have chemistry, we have morphology, but we can actually take it a step further and start thinking about crystallinity specifically.
Okay.
And the idea that there are different forms of crystals that form at
Mhm.
different temperature pressure conditions. And so this work really came out of the fact that the SWAS17b result had come out. And Mark, Sam, and I were chatting, and Sam, being the card-carrying geologist that he is, was like, it actually makes no sense for them to be calling these SiO2 particles quartz, because the paper called it quartz clouds in the atmosphere.
Ah, okay.
Quartz refers to a very specific kind of crystal, and it
Mm-hmm.
is not stable at the temperature pressure ranges that this atmosphere should be.
Key point. Okay.
Um,
Oh, there we go.
yes, I highlighted it there in italics to really emphasize it.
You
It's
get
not.
it across.
So if we
Okay.
look at actually table one,
You want table one. Okay. Let's go
yes,
to table one, low pressure, polymorph.
these are the kinds of polymorphs
Nice.
of SiO2 that you would expect at their particular temperature regimes. And so this is all assuming you're at low pressure. And by low pressure, I just mean less than 1 bar.
Mm-hmm.
Have
Mm-hmm.
our quartz. We have both alpha and beta quartz. And it can tell you the exact shape of it. That's the crystal habit. And then the temperature where that is stable, which is less than around 850 Kelvin for alpha quartz,
Yep.
maybe to like 1150 Kelvin for beta quartz. The density is slightly differs between these different forms, and your refractive index slightly different.
Okay.
So if it's hotter, we actually move into something called tridymite. I go even hotter than that, we move into cristabolite, and then down there, just at the bottom, I've highlighted those glassy or amorphous,
Silica.
which
Yeah.
is actually cooler, but because it's not a crystal, it's tacked on
Yeah.
at the end of
Okay. Very cool. All right.
the
I'm with you.
visualize that. We can go back up to figure one.
Okay. Okay. Good here. Good. Figure one. Okay. Blow that up a bit. Okay. There we go.
So
Oh,
this is now mapping the stability regimes of these different kinds of crystals. So we're looking at pressure on the y-axis, temperature on the x-axis,
mhm.
and those pressures are in something would make sense to an atmospheric scientist like me. So we've got 100 bars
Bars.
low, and then like 10 to the -4 at the upper axis. And the
Mhm.
we're looking at is like 700 Kelvin to almost 3000 Kelvin.
Okay. To the interior, to the, call it the atmosphere.
The upper, yeah.
Okay.
Um,
Mm-hmm.
and then each of these gray highlighted boxes are showing you the stable crystal form at that temperature region. And so moving left to right, we've got alpha quartz, beta quartz, tridymite, cristabolite.
Excellent. Good.
The
Okay.
solid lines are the different substellar objects that I decided to think about in this paper. And so the one that's really driving this is, of course, WAS17b, which is the dark blue solid line.
Mm-hmm.
That's
Mm-hmm.
its temperature pressure profile as determined by that observational paper, Grant et al.
Okay. Okay.
The dotted lines in the background are the condensation curves
Okay.
of SiO2. And so you can imagine that crossing that line is what's going to make you a cloud. So on the right, you have vapor. On the left, you have a condensed particle.
Yes. Okay. I'm with you.
Condensing before any of those gray boxes, you should actually be condensing a liquid particle. And so it'd be melt
Quick
versus
droplets here. Mm-hmm.
yeah. And so if we see that crossing for WAS17b around like 2000 Kelvin at almost a millibar,
Uh-huh.
that the stability region for that crystal should be cristabolite, not quartz.
Okay. Yes. Yes. Uh-huh.
And so then that follows with these other two objects as well, WASP-107b and this L dwarf, that's sort of similar to the one that was observed and modeled in Birmingham et al. 2021.
Yeah, very good. All right. I'm with you.
That's what we're picturing. And so then we can kind of take a step and think a little bit more about these different crystals in particular as we move back down into the text.
Sure. Back off a little bit. And we did table one. Polymorphs?
Yes.
Okay.
So already kind of mentioned this with the figure, but when we're thinking about silicate clouds, we're thinking about atmospheres that are very hot, hotter than 1000 to 1100 Kelvin, meaning hotter than that stability regime for quartz.
Okay. Okay. Mm-hmm.
And so we have to start to think about what are the material properties of these other crystals. And so that was what we really relied on Sam to write this paper as our geologist, because this is not something I was super familiar with
Okay.
before starting this work.
Okay.
Uh, and so the other really cool thing to think about as we dig into this is just how long it takes you to transition from the different kinds of crystals to another.
Okay. Mhm.
Um, and so we discuss a little bit here in this section 2.2, just how these things form, which I've already kind of talked about with their formation temperatures. And this alpha beta transition that's referred to, where you see the alpha quartz, the beta quartz,
Yeah. Hmm.
um, a
Okay.
reverse transition. So you just move between those temperatures. You pretty easily just shift the crystal format a little bit, but you can
Yeah.
go back and forth between them.
Okay. Okay.
When you too hot and you go from not just alpha to beta quartz, but beta quartz to beta tridymite, that's a reconstructive transition. And so you're totally breaking and rearranging those bonds,
Okay.
making
Right.
it's very hard to transition back down. And
Okay.
so if you will eventually transition back down to the lower polymorphs, but it takes very, very long time scales, like 10,000 year time
Oh,
scales.
goodness. Okay. All right.
That means we should hopefully be able to use these particles as tracers of the thermal history of the atmosphere. Because
Ah,
if we see something happen where we see
right.
a transition, that tells us some sort of time scale that it had to happen over.
Cool. I'm with you. Hmm. Hmm.
And scroll down a little bit
Oh, yeah.
more.
There's our long time scales. There we go. 10 to the 5 years. Okay. Good.
And so
Cool.
this actually been done a little bit, not in exoplanets, but on Mars. They detected one of these types of polymorphs, tridymite in particular, in Martian soil. And so that actually is providing evidence that lava from very deep within Mars got to the surface and then cooled quickly enough that it didn't transition to this quartz state, but it is actually present as tridymite on the Martian surface. That was
Cool.
cool as we were digging into this, so that you see this on other planets too.
All right. I'm with you.
And so when we're thinking about the reason that these things are different is because the crystal structure is different. That means spectroscopically, if you have these tiny differences in the bond length and shape, you
Uh-huh.
should expect the spectra to be at least somewhat different.
Yes.
This has also been thought about a lot in protoplanetary disks, and that was actually where a lot of the
Yes. Okay.
third information I could find came from. And so there's a pretty significant history of laboratory studies looking at these kinds of materials um, in these contests where they're heating up the materials, testing how long it takes to transition between the different states, trying to then take that and measure their spectra so that we have this laboratory library of things to compare against.
Right. Cool. Very good. Okay. Cool. Okay. Hmm.
And so we scroll down. A lot of this has been done for the magnesium silicates because that is what we have expected previously, but we
Right.
don't actually have that much laboratory data for SiO2 in particular. And we don't actually expect it to just form directly from the gas phase. What we're actually expecting is a chemical reaction to take place.
Okay.
So we have both SiO and then oxygen
Yeah.
that's probably freed from water vapor, and those react together to make your solid SiO2 particle, which makes it, again, just more challenging to recreate this in the laboratory to then extract those values to put into an atmospheric model.
Right. Okay.
And so my first task when trying to think about are these differences in polymorphs going to be observable was to gather the laboratory data.
Okay. Good.
And so a couple of those already exist for quartz. And so that was already done, which is, of course, why they could use it in the discovery paper for WAS-17b. Even that is a little bit fraught with this paragraph that says G23 take their alpha crystal and amorphous silical properties from this database.
Mm-hmm.
Uh, the databases that do exist just purely because of a lack of laboratory data, are often stitching things together.
Yeah.
So
Yes.
the naming can get a little bit lost in translation as you move from a laboratory person to a modeler to somebody maintaining a database to somebody using something from that database.
Mm-hmm.
Confusion even within this paper that they're calling it an alpha crystal, but it was actually measured as a beta crystal. So once you start to think about the really
Okay.
nitty gritty of these different polymorphs, it gets very tricky very fast.
Mm-hmm. Mm-hmm. Especially if the terminology is different between groups. Yes.
Absolutely. And so although in the paper they actually were using beta quartz, which is probably closer to what might actually be present, they call it alpha quartz.
Yeah.
And I decided to just wash my hands of that and use the values that they stated that they use as a point of comparison.
Okay.
And so I had quartz, had the amorphous silica, and then I had to go and find something to use for beta tridymite and beta cristobalite.
Okay.
And so then I kind of just went in order. I started looking for tridymite.
Okay.
There are a handful here that are listed. There really wasn't anything I could find beyond 2003. And a lot of them, these laboratory studies, are done over very small wavelength ranges, which is just a laboratory sort of constraint. It's hard to have detectors that work across all wavelengths at controlled temperature conditions.
Right. Okay. Mm-hmm.
And so then I was left to choose, okay, what data do I trust the most? And I ended up doing the best that I could. And so the thing that I did was I took these spectra from Lippincott et al. 1958
Woohoo.
from the 50s, because it had the widest wavelength coverage that was relevant to JWST studies. So it covered 2 to 15 microns, which is
Okay.
almost as much as I would want.
Mm-hmm.
It was that they reported their values in physical units. So they gave me like a percent transmission. A
Yeah.
lot of the other studies, as is very common in laboratory studies, give you sort of an arbitrary unit absorption, which is great in terms of a sense of where features are, but it's not something I can actually pull from and make a model out of.
Right. Right. So yay for physical units.
So yay for physical units from Lippincott et al. 1958.
Yay.
These were done at room temperature though, and I know that this is not happening at room temperature. I suspect it's happening above 1,000 Kelvin. So I'd
Mm.
at least try to get something a little bit elevated. And I was able to find that in Satars et al. 2000.
Mm-hmm. Okay.
They were one of the ones, though, that did not report in physical units. They gave me
Okay.
arbitrary units. And so I used the Lippincott data as a scaling factor to the Satars data and was able to sort of cobble together a set of optical properties.
Okay. Okay.
And
Cool.
so what you're actually doing here is you're taking this measured absorbance or transmission spectrum,
Yes.
and then you're going to have to back calculate the optical properties from that.
To get that. Yes.
So you need to know, using the Beer-Lambert law right here, you can get the absorbance from the transmission spectrum, and then you can calculate the absorption coefficient alpha from that, assuming you know the sample concentration that was used and the thickness of the sample. They almost gave me enough information to calculate that from this Lippincott paper. They didn't actually tell me the thickness of their sample. And so I had to do a little bit of guesswork and kind of ballpark it with things I know from the laboratory are reasonable values until I got something that sort of made sense.
Okay.
Pretty significant uncertainty in the thing I calculated because of that, but it does sort of hold together.
Yeah. Okay. Cool. I'm with you.
There, you can calculate an imaginary refractive index K with those values you've already measured.
Right. Or it was the wave number. Yep. Mm-hmm.
So I did that for both the laboratory data sets from Satars et al. And Lippincott et al. Scaled the Satars to the Lippincott to give myself a physical value.
Yes.
And that was how I came up with the imaginary refractive index for tridymite that I used throughout the rest of the paper.
Great. Nice description. Very good. Okay.
I should also note, we don't actually have measurements short of around 5 microns. And so I did have to just substitute regular old quartz for the shorter wavelengths.
Okay, got to do
And
something.
I have really no way of evaluating how bad an assumption that is with the data in hand, but it was the best we could do. And so I just note here, if you're going to try to apply to this to things that are not JWST MIRI, like near spec or nearest or near Kim or
Mhm.
anything Hubble, what I've done here is not going to help you.
Okay. Okay. We'll come back to this point later. Okay. Very good.
So that was for tonight. Then we have to go after cristabolite. Luckily, there is much more recent work that has done this for cristabolite very recently. It's from this Koik et al. Paper,
Mm,
2013. They gave me everything I needed to reproduce that calculation for cristabolite's absorption.
okay.
So from that, you're getting the imaginary refractive index. Then you need the real refractive index. And the way that I chose to do this, which is pretty common, is to use something called Kramer's Kronig analysis.
Yes. Mm-hmm.
And so that's just
Mm-hmm.
essentially an expression you can use to go from one to the other.
Yes. I'm with you there.
There's this very handy open source code called PyEli that I used to speed this up for me so that I didn't have to write a whole routine to do it. But you're just integrating over a really wide wavelength space to go from the imaginary to the real or vice versa.
Very cool. I'm a big proponent.
Point there,
Mm-hmm. Yep.
alpha I is, and so we have those numbers for all of these materials, and so I was able to extract the real data from this.
Very cool. Okay, nice.
So then if we go and look at figure 2, we can actually see the results of all of this laboratory data mining and investigation I did. I think we're going up to get to lab.
Sorry,
figure,
all good. Figure 2.
yeah.
Here we go. Bang.
Yes. So
Okay.
the left plots are the results of that real and imaginary refractive indices that I calculated from the laboratory data compared to each other. So the turquoise there are those quartz values that were used in that original WA17B paper.
Right.
The gold is the amorphous values also used in that same paper. And then the blue and pink are my new values that I've calculated for tritomite and cristabolite.
Huh?
You can kind of see in a way, the peaks are in different places. The strength of the features are in different places.
Yeah.
They're soft, but they're there.
Particularly longer wavelengths. Mm-hmm.
Yeah, and longer wavelengths, which we can talk about later. Real region to focus in on here is that 8 to 10 microns.
Right. So kind of light in there, which is where we got.
Yeah, so since we're on this figure, we'll skip ahead, and once you have the optical properties, the next thing to do is to determine the Me coefficients. And so I'm showing an example of that. Right. And so this is the extinction efficiency, which is related to a Me coefficient here.
And that's Q external.
QX, yeah. It's
Mm-hmm. Okay. All right. So these are the Me scatterings. Okay.
And so, yeah, this is how the Me scattering would work, where extinction is just the combination of scattering and absorption for a particular size of particles. So these are for 32 nanometer sized particles for each materials. And you can see here, if you really zoom in on this 8 to 9 micron region, the peak differs quite a bit between the different polymorphs of SM. And so that's encouraging as we go into the next stage of modeling, is like we are going to see observable differences here.
I was going to say, yeah. Okay. All right. I'm with you. Cool. Okay. So we were down here somewhere coming into Me scattering. Let's see. That was Kramer's Kronig. That, and then we compute the Me with. Okay.
There's a number of different open source Me codes that already exist, and so I just used one of those to calculate those.
Okay.
Now we have our optical properties in hand. We have the Me coefficient database, and we can actually put these into atmospheric models that is going to be the thing we compare to real data.
Okay, cool.
And so the sets of atmospheric models that I have used in this paper are Picasso and Virga. Picasso is for climate and radiative transfer, and it comes from the sort of Sonora family of models that Marley, co-author of the paper, led the development of. And then the cloud portion of this code, of this code pairing is called Virga. And Virga is simply just the Python version of EdiSed, which is a pretty widely known and used cloud model.
Okay.
Uh,
Hmm.
exoplanets and brown dwarfs.
Mm-hmm. Okay.
So essentially, the way this worked was I used Picasso to do the chemistry and radiative transfer, and then Virga to do the cloud side of things.
Okay. Is that a sequential process? So you do the radiative transfer and then the clouds, or is there an iteration between the two, or?
So you could do it iteratively because I knew where I was going. I did
Okay.
not. I just used the out of the the WAS 17B paper,
Yeah.
climate and chemistry, and then
Okay.
add clouds on top. So I
Okay.
didn't iterate here, but you could.
Okay. Okay. Thanks.
So because I was inspired by the WAS 17B results, that was what I compared all of my modeling to, is to these data sets. And
Mm.
so to save myself some time and sort of also benchmark against the existing models that were run for this paper, I reproduced them. And so I used the same chemistry, the same temperature pressure profile, the
Yep.
same planetary, stellar, and cloud parameters.
Okay.
And so I just took their best values as reported in that paper,
Uh-huh.
ran them through my sets of models.
Uh-huh.
And so I'm just talking about here, giving all of those details from the previous paper that I'm also using here. I had to account for the various opacities of all of the gas sources here. Again, use the same ones that are in that original WAS 17B paper. My opacity database resolution is very slightly different, which is driving a couple differences, I think, in the final result, but not
Yep.
very much.
Okay. Okay. Yeah, I'm familiar with that problem. Okay. Very
The
good.
next thing you have to do is account for the cloud formation process. And
Mhm.
so just the
Condensation.
concentration curve of SiO2, which is what you saw way back in figure 1, those dotted lines. This is
Yes.
just the analytic expression of that, uh,
Hmm.
which is important for our cloud model to run.
Yes. Condensation temp. Okay.
Yep.
Yep. Okay.
And so for Virga, we're just doing a pretty simple parameterization here, where if a particle can turn from vapor to cloud particle, we're letting it. We're not
It
thinking about
does.
the efficiency of these things, which could very well differ between the different crystal structures, but we didn't touch that. That is for someone else to pick up and go further.
We'll come back to that. Okay. Very good. I'm with you. Okay. Do, 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 do.
So then here I'm just talking about a couple of assumptions that are built into both the modeling that I did as well as that original paper. We're assuming a log normal particle size distribution for any of the clouds that do exist.
Okay.
And in order to get this really peaky feature that pops out in the data, we need a very narrow size distribution of particles.
Okay.
And so this is a little bit smaller. This 1.2 log normal width is a little bit smaller than the sort of standard Virga run, which would be more like 2.
Okay. All right.
Generate
Okay.
the models that look like the data.
Okay. Well, it's not orders of magnitude off, so we're good there.
It's not orders of magnitude off. And so I just substituted the me coefficients that I calculated
Yes.
with the polymorphs and put them in place of the bog standard quartz value that was already there.
Yes. Okay. I'm with you.
Other thing that I did is because there are very slight differences in densities between the different polymorphs, is I also included that in the modeling.
Ran at different densities.
Yeah, the
Okay.
actual particles should have different densities. And because to calculate the size distribution, we have to do essentially a mass balance and balance sedimentation with vertical upward mixing.
Yes.
We actually care about the density of the particle. So I
Yes.
put that in there as well.
Good. 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 Cool. Okay.
Run the radiative transfer scheme, and you can get yourself to figure 3.
Okay, figure 3, and let's zoom out a little bit and do a global on this one. I'll zoom in as need be. Okay.
The top is sort of the big picture view for all the data that was used in the Grant et al. 2023 paper, and their data presented there is in gray. That's also using data from Hubble
Okay.
at the bluer wavelengths like 0.3 to 1.5 micron.
Mm,
That's percent et al. 2022.
okay. Mm-hmm.
And all of the different models that I ran are all those different colored lines. And so the best fitting model as determined by Grant et al. Is shown there in quartz, in turquoise, but then
Yes.
my new versions are also shown in the different colored lines.
Yes.
The little thing to note here is this blue that goes way down blue lower than any of the other colors. That's because
Mm-hmm.
sort of buried in the Grant et al. Paper, they had to include a lower, deeper cloud deck in order to make their observations match. And the
Okay.
way that they're supposed to do that was by using these AL203 clouds. And so I put them on my model too, and I'm just demonstrating
Okay.
that that's important here.
Yeah, if you take that out, you get something quite low. Okay.
Something very different. And it took me a minute to realize that. And so I wanted to make it very obvious for my readers.
Yeah.
That's what's going on.
Good.
If we then zoom into the lower panel, we can really, you can kind of notice from the top that not much is changing otherwise across all of those short wavelengths. It's only really at the Miri wavelengths where we see differences.
Okay. Okay.
And that, of course, is driven by the fact that I used optical properties that were almost the same for those shorter wavelengths.
Mm-hmm.
But now we're getting into the meat of, okay, I've accounted for these different optical properties, and they do, in fact, look different at JWST Miri wavelengths.
Okay.
So the most dramatic one is the dark blue in that tridymite region, where you can see the peak of the feature around 8 microns is significantly bluer than the others. But there are differences even with cristabalite and quartz as well.
Mm-hmm. Okay.
The other thing going on here is I am comparing both in the solid line and then the dotted line what density does. And so you can
Good.
notice the dotted lines are very, very slightly different than the solid lines, but it's very minute differences. And the
Mm.
reason it's happening is just the densities aren't that different between the crystal structures. What's
Right.
really
So,
moving
table one. Mhm.
yeah, the optical properties.
All around two-ish, two-ish.
Yeah, they're all like 2 point something.
Something. Yeah.
And so the sort of
Mm-hmm.
takeaway here is if you look at that rightmost plot, the particle size distributions you're getting just aren't that different. The
Uh,
particle sizes you're getting differ by maybe 2 nanometers between the different densities. And that's just not causing a big enough difference for us to see it observationally.
okay.
So that
So,
means that
so below some pressure, the distribution becomes uniform. I'm trying to figure out why this line is flat, basically.
the line is flat. That's essentially where you're not
Yeah.
getting significant cloud particles anymore. That's the
Yeah.
stable region for the cloud
Okay.
particles. So they're kind of just disappearing.
Okay. That makes sense. Okay. Got it. Thank you. Mm-hmm.
Yeah, it cuts off. And so you have like sort of this slow decrease as your particles get smaller and smaller as you go higher in the atmosphere, but that's essentially like the cloud base you're seeing there in
Yeah.
that cut.
Right. Exactly. Okay. I'm with you. Thank you. Very good.
So those are the like main results of the modeling work that I did, accounting for all of these different polymorphs. We scroll down a little bit.
Yeah.
Um, Here I'm just noting in the text that discussion about this AL203 cloud layer that I did need to include it.
Right.
But then more than just presenting these models, calculating them, I wanted to do some sort of evaluation of how good the fits were.
Hmm.
And to do that, I just did a pretty simple chi-squared analysis,
Okay.
comparing the data to all of the models that I ran.
Okay.
And then I did a Bayesian information criterion calculation as well to just kind of evaluate the significance of each of those chi-squareds.
Right. Okay. Okay. Mm-hmm.
The results of that are in a table that I think is further along in the paper, but it's essentially just showing you what I've already said, that there are differences in the fit, and although by eye they're pretty obvious, statistically they're not actually that significant.
Okay. All right. Okay.
So then we move on to some L-dwarf models. And so to do that, I did just a very similar thing where I grabbed an existing model data set, specifically the Sonora Bobcat grid, and I just pulled a model that was relatively similar to that previous detection of SiO2 clouds.
Yeah.
So effective temperature of 1700 Kelvin, a log G of 5, and just kind of standard solar metallicity and C to O ratios.
Okay. Mm-hmm.
And so that's a model that exists open source. It's on Zenodo, so you too can play with those models if you want.
Go get them.
I did a similar thing where I just post-processed it with these different polymorph clouds using Virga coupled to Sonora.
Okay. Okay. Mm-hmm.
And so if we scroll down,
Yeah. Okay. WASP 17.
just the discussion here. So we get to figure 4, and this is the results of that L-dwarf modeling. And here I'm not actually comparing to any data. This is more proof of concept to show you that the different models do pop out with noticeable differences depending which polymorph that you use.
Right in here. Yeah. Okay.
Tritomite is the most different, but there are still differences even between the quartz and the cristobalite as well.
Okay. Are all those lines real? I mean, are these lines or
Oh, yeah. I mean, so the beauty of L-dwarfs and
all the spikes here, right?
all the spikes are real.
Okay.
The resolution we might be able to expect from JWST's medium resolution spectrometer. The previous WAS-17 is using LRS, the low resolution, but at medium resolution, you would expect to get something like this.
Okay.
Where, yeah, all of those lines are real. They're absorption from various species, probably mostly water in this range, other than region from 8 to 10 microns, which is dominated by the clouds.
Mm-hmm. Mm-hmm. Very good. Okay.
So,
okay, nice.
Again, this is proof of concept. This is kind of hopefully inspiring for other people to think about these things when they're doing their own analyses of dwarfs and directly imaged exoplanets with JWST's MIRI.
Nice.
So we can scroll down a little bit more.
Go down a little bit here. We got some predictions.
So that's predictions. Exactly what that figure was showing is what we might expect from these different polymorphs. And the whole rest of the paper is discussing where I think this could go.
Okay.
And so if you look at the statistics that I was able to pull out, they're not strongly distinguishing for the WAS-17b results. And so I'm just doing a little bit of a calculation here, suggesting you might need to go to a little bit higher signal noise in order to really tell these things apart.
Okay.
You could do that by stacking multiple transits of WAS-17b. This was just from one transit, but if you got 2 or 3, probably could actually strongly tell these different things apart.
Makes sense.
And then I also note here, that MIRI's medium resolution spectrometer, because it has higher resolution, more like 3000 compared to 100, also to tease these apart a little bit better.
Cool. Okay. And then a little bit beyond,
is the thing that I really got hung up on here that took bulk of this work was the fact that the laboratory data just isn't great. And that I have to be stitching together and scaling. And so it would be amazing if we could go measure these things a little bit more intentionally at the wavelengths we need, at the temperatures we need.
Let's do it. Let's do it.
So this whole paragraph is just a plea to please let's go get these properly so that we can put them into the models, compare to our data, and really believe the things that we're pulling out.
Very good. And who does this kind of work? Who are drivers of these, would do this kind of work these days?
There's a very large laboratory astrophysics community in Germany. So Jenna does a lot of this sort of thing. Where I am now at Goddard.
Okay. Uh-oh. I'll wait till she comes back, I hope. Yeah, you're back. Okay. You froze there for about 10 seconds, so.
Oh, no.
Yeah.
Oh, yes. My internet connection is unstable. I just got to.
Yeah, we froze for 10 seconds, but I'm good. So I heard the group at Jenna was doing this kind of work, and then something about NASA, and then it fell out.
Okay, so NASA Goddard actually has a number of labs with varying capabilities that I'm hoping while I'm here to try to pull together and also make some of these measurements.
Good. Okay. Oh, yes. And then we do have to go beyond me theory at some point.
Yeah, and so everything I did here was me theory, which is assuming that these particles are spheres. But I've been harping on the whole time that they're crystals. And
Yeah.
so by definition, not spheres. And so
First approximation, it's a sphere.
there's approximation. But eventually we do need to probably be treating this a little bit more realistically. And so I'm just pointing to people who have started to do that. And that's, of course, where we need to take this next.
Yeah. Geometry of the crystal. Good. Mm.
The next thing you can think about is I focused very intensely on SiO2 here.
Yes.
But you might imagine mixed cloud compositions. And so that's something to consider. Alkalis are probably really important to actually make tridymite. That was another thing that Sam told us, our geologist, is that you actually pretty rarely should just have tridymite forming by itself. It often needs the presence of sodium or potassium to start to transform into that particular crystal habit. And so you may not actually ever see tridymite without those materials also present. And so that would also be important to
verify.
Doing this kind of modeling.
Very good. Very good. Okay, alkalis, non-equilibrium. Good.
And then the last real meat of this paper is this little thought exercise that I did, thinking about how you might get from liquid to the different kinds of crystal or maybe the amorphous or glassy particles.
Okay.
And so to do that, I'm using WASP 107b as a test case. Okay. And that's because it has this sort of suggestive silicate feature in Miri wavelengths, but it's a specific one. And so you can kind of ask the question, how long would it take for a particle to nucleate as a cloud where that condensation curve is being crossed, where the pressure conditions are right? It can change from vapor to liquid or solid. And then it has to rise through the atmosphere to where we actually observe it.
That's 2 steps.
And so you can do a sort of back of the envelope calculation, which is what I've done here, where you can approximate this vertical mixing time scale, which is just the scale height divided by the vertical eddy diffusion rate, which has been measured for this planet WASP 107b. And I'm just defining the scale height for you. It's a function of the temperature, the composition of the atmosphere, and the gravity. We can relate that back to the pressure, altitude, in the atmosphere, so that we can figure out the difference between the pressure where a cloud is nucleating and where we're actually observing it higher in the atmosphere. And then you can run that example for WASP 107b. So way down figure 1, when I'm showing those condensation curves, you can see that that's happening for this object around 30 bars, very deep in the atmosphere.
Let's go revisit figure 1 while we're on here. Figure 1.
Yeah, so that where that solid teal line crosses the dotted teal line.
Yes. Okay.
So right about 30 bars. But then we're actually observing the cloud way around the other side of that curve around 10 to the negative 3 bars.
Right.
You're in the region there where it should be alpha quartz, but you started as a liquid droplet. And so you can imagine it's transitioned between all of those different stability regions. And so if it's there long enough, it should crystallize as that particular kind of crystal. And so we want to know, how long did it spend in the cristobalite region? How long did it spend in the tridymite region before it eventually got to quartz? And so that's what the back of the envelope exercise is for.
Got it. I just wanted to revisit figure 1 just to refresh a little bit there. And let's slide down to where we were. Going these, and here we go. We were doing the atmospheres. Yep.
Okay, yeah. So we say that happens at 30 bar.
We just looked at this one. Yes.
So, yeah, the rough metallicity and temperature of WASP 107b. And so we can calculate the scale height to be around 800 kilometers.
Okay.
The mean molecular weight, like very conservatively, is no more than 2.8.
Yeah.
Temperatures, 750 Kelvin. And then we're just assuming that our particle's moving at the same speed that the gas is mixing upward. And so it's actually something that was measured by the presence of methane in this object, WASP 107b. And it was a very rapid mixing. So 11.7 log of 11.7 centimeters squared per second. And so put that mixing time scale with the scale height, and get a dynamical time scale for our particle to be around 3.5 hours for a particle to move one scale height.
Okay.
And so we're moving from 30 bars to about a millibar, which is like 10 scale heights. So
Right.
the total amount of time it takes for our particle to nucleate and then be observed is about 37 hours.
Yes. Okay.
We can then break that down, the amount of time it spends in each region,
Yes.
and we can just calculate that difference in scale height. So that means it spends like 2 hours in the cristabolite region and
Okay.
7 hours in the tritomite region.
Okay. Mm-hmm.
That's enough time for that crystallization process to start to occur. So we, in all likelihood, probably have mixed crystals that make
Because it's
clouds.
going up and down.
Yeah. And so we probably have both cristabolite, maybe tritomite, if there's enough alkali stuff hanging around. And so because we have these mixed crystals, it's very possible we're actually spectroscopically seeing that blended out in
That
that.
makes, yeah. Mm-hmm. Right.
This could be true not just for WASP 107b, but maybe also all of these brown dwarfs that we've been looking at, where we're seeing the amorphous particles. It
Mm-hmm.
could be we're seeing multiple crystal forms sort of superimposed on each other.
Yes.
And that's causing it to look amorphous instead of crystalline, but it is in fact crystalline.
Okay. That makes total sense. Yes.
And so then there are other things you can argue with yourself. I've kind of already demonstrated it in that previous section, that you can actually use these clouds as meteorological sensors because they're really sensitively tracing out the thermal structure of the atmosphere based on the crystal that you see.
Okay. Mm-hmm.
You can go further with that. I just did it in this very simple one-dimensional case, but you could think about making that two-dimensional, having your particles evect around the atmosphere as they experience day and night.
Yep.
Uh,
Mm-hmm.
you could also take this further, and I just did this in a very sort of one-dimensional, very parameterized cloud model, but you could put it into a GCM and actually start running global climate simulations here with these particles as tracers. And I think it'll be really powerful, and I hope that people follow up.
A little more expensive of a computation.
Quite a bit more computation. Hope for some cases it'll be worth it.
Oh, yeah. Got it wrong. Very good.
Then another thing to think about is how this might apply to lava worlds and sort of real planets that maybe have silicate vapor that's then very quickly settling out onto the surface. And you could, in this same sort of regime, maybe you would expect silicate clouds. And I think you should also account for these different polymorphs in that case. And maybe it's like in that Martian detection of tritomite, it could also tell you something about the interior and the thermal structure of that like sort of subsurface.
Yes. I'm going to come back to this point. Yep. Okay, cool.
And then the last thing to realize is that I have focused entirely on SiO2 throughout this.
Yes.
But almost all minerals have polymorphs. And so anytime you're talking about a mineral cloud, you probably should also be considering whether or not there are polymorphs and what they do about the atmosphere. So sort of touched on a couple here that I think would be most important. So the magnesium silicates that we expect to exist in a lot of atmospheres do have different crystal polymorphs. We don't think for forsterite there are any that should exist at these low pressures. So you can probably safely ignore that for the Mg2SiO4.
Okay.
But for MgISO3, there are several different polymorphs that exist. So that's clinoenstatite, orthoenstatite, and protoenstatite.
You say that really well. Very good. Here we go.
The laboratory studies for these materials are even more sparse than for SiO2. And so that's also laboratory work that needs to be done.
Okay.
We can also think about ZNS, which should be
zinc,
Galerite and worksite.
Here we go.
And so measurements of this do exist, and they're kind of used interchangeably in the exoplanet literature right now. And so I hope we stop doing that and focus in on that's probably appropriate to the particular physical regime that we're in.
Okay.
We can also then think about TiO2 particles. They're probably not observationally going to be super important, at least based on prior work that's been done, led by Peter Gao et al. 2020. But there are multiple types of polymorphs there. And again, various databases use different polymorphs for each. And so we should just be really particular about which ones we're thinking about. And then the last one is Illumina, this AL203 cloud. There are a number of different metastable polymorphs that exist for this, but probably there's only one that should be relevant for exoplanet atmospheres. And so that's actually probably good news, is that we don't have to account for all of these different polymorphs. Although I've tried to prove that they can be useful, it also could be just a lot of bookkeeping.
Yes. Okay. Very cool. And then a little bit about the observations.
Yeah. So this very last point that I touch on here is the idea of being able to use MRS to get after these long wavelengths. You noticed way back that in figure 2, I believe it is, that there are actually really strong differences in the polymorphs at the 18 to 24 micron region.
Yes.
And so JWST MRS does technically have detectors that go that far. The problem is that the combination of the flux drop off, you're just not getting that much emission from these objects at those long wavelengths.
Right.
And the noise, just your sensitivity from the detector itself is a lot lower. Okay. So probably unlikely you'll be able to make these measurements with MIRI MRS. Just this combination of noise and flux are not favorable.
Okay. Well, that'll be exciting to see. Okay.
So then that brings us to the summary, is just we're trying to pull this idea of polymorphs accounting for the different crystal structure of the clouds into the exoplanet literature. Protoplanetary disk people have been thinking about this for a long time, and we should follow their example. I've tried to sort of demonstrate why here it's important, show you kind of a pathway of going from the laboratory studies that exist, taking that into something you can put into a model, modeling it, and comparing it to the observations.
Right. Cool. The whole pipe. Very nice.
And so then
go ahead.
Table 2 is just the full breakdown of all of the statistical fits that I ran against those various models.
Right. These are the BICs.
Yeah, so to determine exactly how significant those are, which for the most part is not particularly, just with the data we have in hand.
Right. Yeah. Okay. Very cool. And then we got a couple of appendices. Don't know if you want to talk about them. We'll just mention them.
Yeah. So the first appendix, or the second appendix, I guess, is Appendix B, is just showing you the importance of picking particular optical properties. And so this is comparing whether or not you use those 1958 optical properties for tritomite to the 2000 ones, which is the figure on the bottom. So if you compare the two blue lines there, you can see they are different.
Yes.
And so thinking about this, like this is going to drive your model fits. And so it's just important to figure out which laboratory data you trust. And it's also demonstrating the importance of temperature dependent measurements.
Yeah. Cool. Very cool. And then some extended runs on WASP 17.
Yeah. And then this extended set of runs is where I, in the process of doing this modeling, kind of went down a little rabbit hole and said, what if you try to find a solution that doesn't involve this deeper cloud deck?
Yes.
So I was actually able to recreate some model runs using any of the SiO2 clouds. This is just showing an example of tritomite. But if you tweak just how quickly particles sediment out, that's that F value, sedimentation efficiency, the best fits from that previous paper. And what the bulk of the main text is focusing on is this F set of 0.3. Which doesn't match your optical slope here. That's that difference between that light blue and the dark blue at the short wavelengths.
Yes.
That you don't recreate that without a deeper AL203 cloud deck. But if you tune the F set up and make it 3, which is very, very high, we don't expect that in hot Jupiter atmospheres. You can actually get a much better match.
Okay.
You're sort of moving out that, like maybe take a moment to consider all of the phase space that is available to you as your tuning model parameters to make sure you're not ignoring one that could
Mm-hmm.
answer. You then have to ask yourself if it's physically realistic, and I'm not totally convinced by
Right.
this, which is why I buried it in the appendix. But it's kind of an
That's
interesting
good
little,
study to do, though.
yes.
Absolutely. Very cool. Very cool. Beautiful, beautiful work. Sarah, I want to thank you so much for walking us through your very awesome APJ letter.
Thank you so much for having me.
Sure. And it came up several times. In fact, I really admired the whole section there on challenges. And certainly, I think one of the biggest one is just lack of laboratory data. Right, that's really where the call has to be. So do you potentially see this getting better in the next few years? The other comment I'll make is or at least what I saw in there was, we had solar compositions, we multiplied by 10 solar compositions, and the sensitivity of some of the formation of those clouds to the actual composition, right? And so solar is an assumption.
Yes.
Um, and so, how do we go about maybe nailing down something a little more precise for the composition of the object? So, future directions. Where do we go from here?
So on the laboratory data side, I'm actually really hopeful. Any of the measurements we need at temperature, at the right wavelengths, all of that is very possible. No one's just been particularly motivated to go take the measurements yet. And so
Until
I hope I've proven here, yeah,
until
this
then.
is important. It is doable. We should go do it. And so I'm very hopeful in the next couple years, people
All
are
right.
going to start taking these measurements. I
That'd
might
be
be um, and then in terms of the metallicity dependence, that's tricky, but I think we can get there with a combination of things. So you have this degeneracy between the strength of your features from the gas abundances, but then also the presence of clouds could kind of similarly shrink or
okay. There.
um, drive up the size of your features. So if you have both cloud measurements in the mid infrared as well as gas phase measurements in the near infrared and the mid infrared, you can get those things together and give you a
Yeah.
better understanding of the metallicity of the object from the gas phase, and then how that feeds into the cloud.
Okay. Okay. Very nice. Cool. It'll be really exciting to see both of those develop, but particularly the laboratory measurements over the next couple of years. Be really cool.
Yeah, I'm excited to see.
Yeah, be really nice. Sarah, thank you so much for walking us through your very lovely article.
Thank you.
And that will do, everyone. And I hope this made your astronomy day or laboratory astrophysics day just a little bit better. And we will see you on the next one. Bye bye.
Bye.